Hi there. We saw in class this week how we can take any real number and treat it as an angle, and we're able, using angles in standard position in the Cartesian plane, to calculate the sine, cosine, or tangent ratio, any one of the trig ratios for that particular angle. Well, if we think about that for a moment, it means that we can take any real number we like, thinking of it as an angle, we can calculate a sine, cosine, or tangent of it, meaning that we've got an input that's a real number and an output that is some other value. We've got a function here. So, for instance, we can talk about the sine function, y equals sine of x. We take our favorite real number x, and we can calculate the sine of that x if we treat x like an angle. So if you were to draw x equals negative 2 pi in the Cartesian plane, so it'd be a full revolution in the clockwise direction, we'd get a terminal arm back on the positive arm of the x-axis. And if we calculate the sine ratio for a point on that arm, say the point 1, 0, we would get a sine ratio of 0 there. Then for negative 3 pi by 2, we'd have a value of 1. At negative pi, we'd have a value of 0. And you could calculate the sine ratio for all these different angles I've got listed here. Now, if I were to draw the graph of y equals sine of x, see that the y values of 1 and negative 1 are important. In fact, those are the largest and smallest y values, respectively, that are possible for the sine function. And what have we seen here? We've seen that at x equals 0, y is also 0. At x equals pi by 2, y is 1. And so on. We can choose a few points on this sine curve. And it turns out if we were to fill in all the points in between, we get this nice smooth curve. Now this is only a piece of the graph. This pattern goes on and on forever. Okay, but it just repeats itself. It's a periodic function. So that's y equals sine of x. Now you need to memorize this. You're going to have to memorize all the graphs in this video. They are prototypes. And we could, of course, comment about the properties of this function. So the domain is going to be all real numbers. The range, well, we can only have y values between negative 1 and 1, but including those values. And the intercepts, well, for the y-intercept, we get 0, 0. And for the x-intercept, well, don't worry about that. There's going to be infinitely many of them. It's a bit complicated for now. Let's move on and take a look at y equals cos x looks like. Okay, so again, exact same setup. Every real number can be thought of as an angle in standard position in the Cartesian plane, and therefore we can calculate its cosine ratio. We've got a function. So if I take negative 2 pi and plug it into my cosine function, I get a value of 1. Okay. Then I get 0 at negative 3 pi by 2, negative 1, 0, 1. We see the rising and falling nature of this cosine function. And I can draw it. It's going to have a very similar shape to the sine function. In fact, it's exactly the same as the sine function, except it's just been shifted pi by 2 units to the left. So again, this is going to be a prototype that you'll have to memorize. You could put it in the back page of your notes where you keep all your graph prototypes. Notice here that there are 4 ticks on either side of the axis in the kind of traditional way in which I draw this. That'll come into play when we talk about graph transformations in class this week for trig functions. Again, this graph, this is just one piece of it. It goes infinitely far off to the left and right, always having this wave pattern here. So that's y equals cosine of x. Again, you have to memorize this. You should draw it in the back of your notes on the graphs page. We can comment on the domain and range. It'll be the same as the sine function. Now the y-intercept is going to be different now. We see that it's at 0, 1, but the x-intercepts, again, there's infinitely many of them. We'll just leave that for the time being. Now, if we look at this function, as I say, it repeats. If we take a look at trying to find the smallest piece of it, that if we just repeated that part again and again and again, we'd get the whole graph, I could say take the piece that goes from here to here. If I just cut out that piece and just copy it again and again and again, I get the whole graph. Now the length of that piece is 2 pi. And that is what we're going to call the period of that function. Okay? It's, if we just repeat any piece that has a length of 2 pi, we just repeat it again and again, we get the whole graph. And if we look up at our sine function, it has the exact same property. If I take a piece of width 2 pi, any piece I want, and I just repeat that piece over and over, I get the entire graph. So you notice that there's a lot of similarities between the sine and cosine function. There's a few differences, but basically they have the same sort of shape, just one is a shifted version of the other. We'll talk about the tangent function now, and it is very different. So if we look at the tangent graph, here, if I calculate tangent of 0, that'll be 0. And here the tangent of pi by 4 is going to be 1. The tangent of pi by 2 is really weird. It does not exist. 3 pi by 4 will have a negative 1 value, 0. So we have a very strange function here. Sorry, that's positive pi by 2. Put on some of my points here. Now what's happening where our graph doesn't exist? We actually have some vertical asymptotes. We have our graph shape kind of coming up and heading towards that vertical asymptote there and looping down towards that one there. Here's another branch here. Of course, there's infinitely many of these branches. Do a better job than that. There we are. So there's y equals tan of x. It has infinitely many separate pieces. Okay? We can talk about everything about it is tricky. Well, the domain is tricky because we have infinitely many pieces. There are infinitely many holes in the graph. The range. This is one of the few ones we can comment on. It goes from negative infinity to positive infinity. The y-intercept, again, that can never be that challenging. It's at 0, 0. And then the x-intercepts, again, is tricky. There's infinitely many of them. Now, if we look at this tangent graph, we notice something slightly different than the sine and cosine graphs. If I take a piece of width pi here, okay, from negative pi by 2 to positive pi by 2, that width is pi, and I just repeat that piece over and over again, I get the whole graph. So the period of the tangent function is pi, whereas the period of the cosine and sine functions is 2 pi. So we're going to make a little comment about this. So the period of the sine and cosine functions is 2 pi. The period of the tangent function is pi. We're going to talk a lot about period when we're talking about our trig functions and our graphs. Now the amplitude, we only talk about these for the sine and cosine functions. What it is, it's half the length of the range of the function. Or another way to put it, it's the distance between the midline and the peak or the valley. So it's 1 unit to go from there to there. Or, on the other hand, it's 1 unit to go from the midline to the valley. Okay? And the same thing is true of our sine function there. Okay? We have 1 unit to go from the peak to the midline, or 1 unit to go from the midline to the valley. So we call that the amplitude. So for our sine and cosine functions, the amplitude of those functions is 1. Now this may seem like a little extra bit to remember, and it is, but we're going to see when we do graph transformations, we can use amplitude and period to make our graph transformation work a lot simpler. Okay? So it's worth our while to know those key little facts. So we'll memorize those. And of course, I'd like you to also memorize the graph of the tangent function. You can put it in the back of your notes. All right, thank you very much.